So thank you, Jesse, and thanks for an excellent organization and all the help you have rendered. So today, do we need these lights off or is it okay? Fine, okay. So today the title of my talk is something about the atoms of space-time, which none of us have seen and most of you would not have heard unless you read this e-print. And I would like to try to convince you that this is for real and it helps us to understand the nature of gravity. So let me begin by asking a question about gravity. Many of us, for the working on this kind of a theme for the last 1 decade or so, and I think there is fair amount of evidence today that classical gravity has the same conceptual status as elasticity or hydrodynamics. Since I have given so many conference talks on this, I am going to take this as read. The question I want to address today is why? Why is it that gravity has this strange affinity to thermodynamics at some level or the other? How do we understand this macroscopically and microscopically? Let me explain what I mean by this why. If you had Newtonian gravity and somebody told you that the acceleration of particles are independent of its mass, it's very easy to take care of that. You say the inertial mass is equal to gravitational mass, take it or leave it. And once you take it, the acceleration will be independent of the mass, end of story. And you can say that's it. But we know that is an unsatisfactory explanation. There is a deeper level of explaining that by saying that gravity is the curvature of space-time and particles follow a geodesic in that space-time. And geodesics in the space-time don't give a damn about what the mass of the particle is, as a result of which all particles will follow the same acceleration. So there is a deeper layer of explanation. In the same spirit, you can just say that, well, gravity is peculiar, it has some thermodynamic affinity, end of story. What I am looking for is a deeper reasoning as to why there is a connection between gravity and thermodynamics and why gravity looks like an emergent phenomenon. The summary of the talk, at least part of the summary of the talk, is given here. The reason is very strange. If gravity is immune to the zero level of energy, shifting of the zero level of the energy, then it must have a thermodynamic interpretation. This connects two concepts, one loosely talked about in the context of cosmological constant problem, etc., and the other which is the thermodynamics of gravity. And it says that these two things are deeply related. That is what I will be trying to convince you in the first part of the talk. That would be essentially the macroscopic explanation. I will show you how you can obtain the field equations of a wide class of theories of gravity from the entropy, maximizing the entropy or the heat density of matter on null surfaces. So those of us who have forgotten thermodynamics, which we took in our undergrad days, heat density is what distinguishes thermodynamics from Newtonian mechanics. Everything has energy, but thermodynamics also has a free energy. The difference between these two is exactly the heat content. Heat content for a unit volume is the heat density, which for all practical purposes is the entropy density. So what will happen is that the field equations will get obtained from maximizing the total heat density. It leads to a very wide class of gravitational theory, and the form of the entropy density decides the theory. Exactly like the form of the entropy density decided whether you are talking about a metal rod or a glass of milk. Second, once you do that, the evolution equation for gravity can be given a completely thermodynamic interpretation, and you will find that there are suitably defined surface and bulk degrees of freedom, and the difference drives the gravitational evolution. And in all static geometries, there is some kind of a holographic equipartition between surface and bulk degrees of freedom. In this approach, gravity responds to what is known as the heat density. And again, those of you who remember it from undergrad days, there is something called a Gibbs-Duhem relation, which says entropy density is P plus rho. Cosmological constant is the only creature which has zero heat density. So in this approach, gravity does not respond to cosmological constant. It responds not to the energy density, but to the heat density. And the cosmological constant need to be fixed as an integration constant. Could I take the questions at the end? Okay, thanks. Yeah. So some of the questions might get answered as I go along, and so it should be better to take it at the end. And I will show that its value is actually determined by a conserved quantity. Okay, so this is the macroscopic story. What is the microscopic story? I will show that there is a very natural way of defining what I call the distribution function for atoms of space-time, and that will give you the microscopic origin for the same heat density. And this arises because of a very strange result which we recently discovered, that in a renormalized space-time, each event or a point has zero volume but finite area. I'll explain how that comes around. Okay, that is the summary in case I didn't get to the end of the story. Now let us get started. So I want to start by building gravity brick by brick. So there are two distinct parts to gravity, which is the kinematics and dynamics. And there is a very understandable concern in the community for anybody tinkering with general relativity, because it is such a beautiful theory. So I want to first reassure you by saying that all the beauty and elegance of gravity comes from the kinematic part, not from the gravitational field equation. They are pretty ugly and we don't even understand where it comes from. So I'm not going to touch this. That will remain intact. So all the beauty and elegance will remain. In addition, I will give you a nice principle to get the dynamics. So here is the kinematics of space-time. So you take an arbitrary fixed geometry, you don't care what equations it satisfies. So these are the light rays, and you go to the local freely falling frame around this event. So the light rays, which are some arbitrary curves, become 45-degree lines there in that local region where the inertial frame exists. And you just postulate that the laws of special relativity is valid in this region. For me, as far as matter sector is concerned, I just need a stress tensor, and the special relativistic conservation generalized to curvilinear coordinates and then to curved space-time by principle of equivalence gives me the matter equations of motion. So I just have a conserved TAB for me. What is remarkable here is that any coordinate system and any set of observers is allowed. And this is serious business, because it tells you that unlike in special relativity, we need to take non-inertial frames pretty seriously. And that leads us to what I consider to be the most beautiful result we have in this subject, which says that if you have an observer who have part of the region of the space which is inaccessible to him, he will attribute a temperature to that space-time, which is related to some suitably defined acceleration, except for fundamental constants. This temperature is completely independent of the field equations of the theory. I don't need to know where that geometry comes from. You just give me a geometry and you have a class of observers. If he has a horizon, there is a temperature. It is just like, again, a glass of milk and a metal rod can be kept at the same temperature. Temperature tells you nothing about the dynamics. It is purely kinematical. So this is the classic example. There is an accelerated observer in flat space-time, and he will attribute a temperature. There is a very well-defined, precise, order by order local version of this, which I call local Rindler observers. This was the creation of Ted Jacobson. That at the same point where you have inertial frame, you can also have a guy nicely sitting there who is accelerating with respect to the freely falling observers. What happens is that the local vacuum state as defined with respect to the freely falling observers will look like a thermal state as far as this guy is concerned. This is the local version of the Unruh-Davis effect, and it's a very non-trivial equivalence, especially when you do it in a local region. What it tells you further is that we now have one more constant in, because this temperature comes with a H cross, so I have H cross and C in the theory, nothing else, but two fundamental constants. There are also two more results I need about the local Rindler horizons to proceed further. The first is that if you go here and if there is some matter which crosses this local Rindler horizon, it will have a heat transfer to the horizon, and that is given by the matter energy momentum tensor dotted with the normal to that null horizon, which is a null vector LALB. So this is the heat density of matter. The second result which you need to remember, because we will come back to it much later, is that if I take a Euclidean extension, the null cone, which is the 45-degree line x square minus t square equals 0, goes to x square plus t Euclidean square equals 0, which is the origin. So what is happening here is that you have a hyperbola of the accelerated observer, and that hyperbola, as it goes closer and closer to this 45-degree line, in one limiting case it reaches this. And this pink region which is shaded is this region, and all that goes to a point. So as you approach the origin in the local Euclidean version, you are approaching the null surface. So the origin selects out the null surfaces. Just remember that for future reference. Okay. Now we go to the dynamics of gravity. And as I told you, we do not have a guiding principle in conventional approach to GR, how to write down the dynamical field equation. I would like to state that this should be the guiding principle. The matter equations of motion, we know, remain invariant if you add a constant to the Lagrangian. It's only the derivatives of the Lagrangian which matter in matter equations of motion. Let's not worry about supersymmetry for a moment. I postulate that gravity must respect this symmetry. Gravity shouldn't go around breaking a symmetry which already exists in the matter sector. It turns out that this is a very powerful demand, and let me explore its consequences. Mathematically, this means that the variational principle which you use to obtain the dynamics of space-time should remain invariant under TAB going to TAB plus a constant times delta F. This must be a symmetry of the theory. Okay, this is equivalent to adding a constant to a Lagrangian. So this immediately tells you that you cannot have metric as a dynamical variable varied in a local generally covariant action. There are formal proofs of this theorem, but trivialist way to think about this is in any such local action principle you will have a L root minus G. If you add a constant, that constant will couple to the root minus G. It's the same old cosmological constant issue. So you can't vary the metric. Well, but then you seems to have a problem in your hand. Your variational principle, after all, it has to have TAB as a source. It should finally constrain the metric, and there must be some auxiliary variables which you can indeed vary in order to get the equations, because you can't vary TAB. But normally when you vary something, you get equations of motion for that variable. But now you have to vary QA and get equations of motion for GAB. How do we do that? Second, it has to depend on TAB in some form, but if I add TAB to TAB plus a constant times delta AB, this variational principle should not change. How do I take care of that? The answer to both of them are the same. There is a minimal set of degrees of freedom which you want to throw in order for this variational principle to be well defined. What you do is you take a null vector field as that minimal auxiliary field, and TAB, NA, NB is the way the matter source appears there. Then I want to, since this is like the heat density of matter, you want to come up with a form for the heat density of geometry such that when I vary this null vector NA here and demand that it should hold for every null vector, because no null vector is specified, we have just thrown in as an auxiliary variable, you should get an equation of motion which constrains the background geometry. So roughly speaking, this is what we would expect, because this adding a constant to this should get absorbed by an integration constant. We also need, since this is conserved, this is constant, this object, whatever it is, to satisfy this equation. The non-trivial question is there any such functional which will satisfy this criterion? This is very non-trivial. It is not even guaranteed to you that this variational principle will work and has non-trivial solution, and what it would do. It turns out remarkably that you can do that. This was known for some time. What you should take is just take a quadratic in this derivatives of this null vector field, because you had this null vector field here, and here you throw in this quadratic with a tensor P ABCD which has this particular structure. It's a product of Riemann-Christoffel curvature tensors multiplied by a determinant tensor. For dimensional reasons, you add an area here, which right now is an unspecified constant. If you do that, the resulting field equations, it does constrain the background geometry. The resulting field equations has this particular structure. There is a geometrical object here. This is the trace of this, and then it is sourced by this, and there is an arbitrary integration constant in the form of a cosmological constant, which we will come back right at the end. Now, these are known. These are called the Lankos-Lovelock models of gravity. They are very beautiful. They work in d dimensions. In d is equal to 4, it uniquely reduces to Einstein's theory. What is more, in arbitrary d, these are the only class of field equations. It doesn't like me. Okay. This is the only class of field equations for which you will find that the equations of motion are still second order in GAP. Remember that the variational principle has a string of curvature tensors. So, you would have normally expected the equations of motion to be higher order, but this particular structure is such that it has only up to second order in metric tensor here. These are known previously and is another way of deriving this. But now we have to interpret this result. So, I have brought in heat density for gravity, so to speak, but I haven't proved to you that it is heat density anymore. It is just a variational functional. Okay. So, I will come back to that as well. In this particular case, it is an integration over null surfaces, of which Na is a normal. Okay. This Na is a null vector which was introduced. This Na, if you take any null surface for which Na is a normal at a given event, that is good enough. But even if you take it as a 4 volume, the same principle works. Okay. So, macroscopically, we had this Na and we have to interpret Na. This is related to his question. Macroscopically, you can do everything by taking a class of null surfaces in the space-time and identifying Na with the normals to the null surfaces, and taking this Hxi as the heat density on these null surfaces. Microscopically, I am going to eventually, at the last part of the talk, interpret this as a distribution function for atoms of space-time with a velocity equal to Na. So, we will come back to it later. So, let us finish off this macroscopic part first. So, where is the thermodynamic connection? I started with the postulate that the theory should be invariant and TAB going to TAB plus lambda delta AB. Then I showed you that you need a null vector to make sure of this. Then I also pointed out that there does exist a gravitational heat density which will give you decent field equations. Now, there are several ways of doing this. Macroscopically, you identify this with LA, and this is the answer to your question. This integral is over a null surface with a parameter lambda for this LA, and this is the 2 metric and d2x, and these are the 2 Hg and Hm. And this will be interpreted as the total heat density of the null surface. What we are saying is that if you extremize all the heat densities in the all null surfaces simultaneously, or all null surfaces going through a point simultaneously, it leads to the gravitational dynamics of a very, very general kind. You can do something better. This object is known in Lankos-Lovelock theories, and I would like to call it the entropy tensor of the space-time. The reason is that it has been shown earlier on, this is something closely related to what is known as the walled entropy. If you take the field equations, construct any sensible horizon like a black hole solution, and you calculate what its entropy is, its entropy will be given by this tensor multiplied by 2 binormals at that surface. So, this is for students in the audience who are not familiar with this sort of a thing. There is a usual myth that the entropy of a black hole is proportional to area, and many people seem to think that there is a very general result. There is not a general result at all. It is very specific to Einstein gravity. So, if you go to more generalized theories of gravity, you get an entropy density which is much more complicated. But what is remarkable is that the on-shell value of whatever you have been extremizing is exactly equal to the heat density on that surface. So, I kept saying I am extremizing something, it is a thermodynamic variational principle, and here is the proof. Because after you have extrematized, you ask what its value is, and its extremum value is just the heat density, where this is the Andrew-David temperature and this is this entropy density. So, it works for all theories, not just Einstein's theory. It will pick up the correct entropy of the theory, and the entropy in turn determines the theory. So, there is a two-way crosstalk between the two. Okay. Now, we want to go a bit further. It is a little silly to say that I have a thermodynamic way of looking at gravity and finally write down Einstein's equation. Einstein's equations are not thermodynamic, they are geometrical. So, if I have a thermodynamic theory, I should be able to write down in my entire dynamics in thermodynamic language. And I believe that is the way to proceed, and I will tell you where it comes from. So, the first thing to ask is, in normal thermodynamics, what happens? There we have this beautiful result by Boltzmann that if you can heat something, you don't have to think of it as some calorific fluid or any such nonsense. Heat is a kind of motion. There are microscopic degrees of freedom, and its motion is what we call heat. In particular, there is a remarkable relation you can write down in normal thermodynamics. Normally, we are misled by writing this equation as E equals half nkt. That is wrong. We should write it as n equals E by half kt. The reason is that when you write it like this, the right hand side can be defined entirely in thermodynamics. Energy exists in thermodynamics, temperature exists in thermodynamics. Left hand side simply doesn't exist in thermodynamics. It is infinity in thermodynamics. Number of degrees of freedom recognizes discreteness of the system. Thermodynamics does not recognize the discreteness of the system. Statistical mechanics does, but not thermodynamics. So this relation is a direct connection between microphysics and thermodynamics. And in fact, people knew that they can count something like Avogadro's number even before they knew what they were counting. And
I'm sorry, but just please stop for the moment.
okay. Okay, so what I was telling was that this is a relation which connects macroscopic thermodynamics with the number of degrees of freedom, which I will always call the number of atoms. Okay, just a way of speaking. Can we do this for gravity or space-time? Because this guy said that if you can heat it, it must have microstructure, and you can count how many degrees of freedom are there in the microstructure. So we can heat up space-time. So can we count this? It turns out you can, and that is extremely beautiful. Because as I said, there is no point in writing down the field equation in geometrical language if I am going to take a completely thermodynamic approach towards space-time. This is why I don't have much sympathy about thermodynamic derivation of Einstein's field equation. Einstein's field equation is a field equation, while we want a thermodynamic relation. So how do we express everything in thermodynamic language? That brings in a very nice idea. Firstly, if you take static space-time, I mean this is related to Ram's question as to if there is equilibrium and equipartition, what happens. If you take static space-times, then you find that the bulk energy in a region is related to, can be written in this form, which is this area element divided by that constant which we thrown in, which comes like a quantum of area. This is the number of degrees of freedom dn, and this is the local Andrew Davis temperature. So E is equal to half dn kt integrated over the thing. And this again extends to all the Lovelock models with the correct dn, which now depends on the entropy tensor. So let me try to present this in a slightly more graphical way. Take the normal space, assume everything is static and in equilibrium. Then you have a surface here, which is just the two-dimensional surface of a three-dimensional region. You attribute a particular number of degrees of freedom, area divided by that LP square to that. There are normals to this, and there is gravity acting downwards. And you have observers sitting all over this surface who are locally accelerated compared to the freely falling observers at the same point. You can define a local Andrew temperature at any point, and you can also define an average temperature around the surface. Think of this surface as a microwave oven kept at this temperature. If matter is in equipartition with this temperature, I am not saying it is, but if it is, then the number of bulk degrees of freedom you will attribute to the piece of cake kept inside this microwave oven to bake will be this energy divided by half kT of this average temperature. So this is just a way of measuring the total amount of energy there, which happens to be the Komar energy. What you find is that if the space-time is static and in equilibrium, this n bulk and this n surface are equal. This is just a graphical way of saying what I just now said as an equation. So there is a correspondence between bulk and boundary degrees of freedom in all static space-time geometries. But then we don't want to imagine equilibrium, we don't want to assume equipartition. This is again in relation to his comment. What happens if there is no equipartition or equilibrium or any such thing? Then it turns out that the evolution is very naturally represented in terms of these variables. This is metric and this is Christoffel symbols. And these two variables themselves has interesting thermodynamic description, which I won't go into, but you can find it here. But in our context, the space-time evolution, the dynamical content of Einstein's equation, can be written very nicely as follows. The time derivative, this is the time-like vector normal to the foliation surfaces. Essentially, the time derivative of the momentum is given by the difference between n surface and n bulk. If there is an equipartition between n surface and n bulk, time evolution ceases. If it is not there, this is what drives the dynamics of the space-time. It can be shown that this equation is implied and implied by Einstein's equation. So this is completely equivalent to Einstein's equation. If this equation holds on all surfaces, then it is equivalent to Einstein's equation and vice versa. So this is the natural way of thinking about Einstein's equations or any geometrical field equations in this thermodynamic language. It is essentially the difference between the surface and bulk degrees of freedom which drives this. It is also rather interesting to see how Newton's law emerges from it. There is something interesting there. We have introduced just these three constants into the theory. One area, C and H cross. The temperature gave us this and entropy gave us LP square. And the Newton's laws of motion will be m1 m2 upon r square multiplied by this. You should resist the strong temptation to call this some capital G, which is independent of H cross. It's not independent of H cross. You can't keep G, H cross and C as independent variables. The independent variables of the theory are C, LP and H cross. And the H cross going to 0 limit doesn't exist. Gravity is intrinsically quantum mechanical at all scales, just as this piece of plastic is intrinsically quantum mechanics at all scales. You take H cross going to 0, every atom in this piece of plastic will collapse, it will not exist. You take H cross going to 0, every atom of the space-time will collapse and space-times will not exist. So that is brought in very nicely the way these things come in. The H cross could have come on top, it doesn't. I mean, the way you introduce this in the most natural way, LP square sits on top. Fine. Now there is also one more thing which, well, we don't know how much time I have, so I can go on and on. That is good. Okay. So, okay. So it also turns out that there is a very natural way of defining a momentum for gravity as measured by every observer in this theory. And it just turns out that that momentum plus matter momentum being conserved for all observers is equivalent to field equations. The reason I brought in is that in that sense, that momentum allows you to define the variational principle in a natural way. More importantly, the projection of this momentum on any null surface. There are three natural projections of this momentum, and that leads to three different equations. One is a Navier-Stokes equation. This is a generalization of the old result by Damu that gravitational field equation projected on a black hole horizon takes the shape of a Navier-Stokes equation. This results hold for any space-time for any null surface. It gives you a Navier-Stokes equation. You can also write it in this way. This is not Clausius relation. It is something more complicated which you can read up here. And the third way, which I have not written but which is related to a comment which came up in the discussion, is that if you have a null surface, there are some important issues about Cauchy condition for that. You can either evolve it like this or you can evolve it like this, and this gives you the evolution equation for the null surface along the null rays. Fine. So that is the first part of the talk. Now I want to get to more exciting stuff. Some of these what I have talked so far, you might have read in my works or you might have heard me talk about this. What next? You have a way of looking at, you start with a guiding principle, you go forward to macroscopic scales, and you have a way of interpreting gravity in thermodynamic language. But we want a deeper understanding of this from a microscopic scale. Just as we have a deeper understanding of thermodynamics from statistical mechanics of atoms and molecules. Firstly, we want to understand this auxiliary null vector field Na which I just threw in, and then identified it with a null surface. we want to understand why these null vectors are selected out. I mean, I know that it is blocking information in some sense, etc. But as we were discussing, these are all sort of vague notions because these are only patches of null surfaces. So we want to know where the null vectors are selected out microscopically. And of course, this happens to be somewhat easier. You have to get the explicit form of this heat density of gravity. How do we do that? Further, we need to recognize discreteness of space-time because the LP square tells you that there is discreteness. But we should be able to use continuum mathematics because we really don't understand how to do completely discrete structures. How do we do this? It turns out that we have all been taught how to do this, except that it was never emphasized, and as a result of which we never learned it in that form. If you take a normal fluid, flowing water or a cup of coffee, there are two layers of description you can use for this. This is Landau fluid mechanics and Landau physical kinetics, standard stuff. One level, you introduce things like density at t and x, the velocity field of this at that time, then pressure, temperature, etc. And you write down your Euler equation, continuity equation, etc. and you do fluid mechanics. At that level, you ignore the velocity dispersion and you ignore discreteness. It is continuum all along. It is continuum fluid mechanics. But we also know there is another description, which is the description of physical kinetics, where you actually say that the number of molecules in a phase volume d3x, d3p is given by this distribution function. This is a discrete description, and good textbooks, like I said, Landau, will tell you, be cautioned that d3x is practically infinitesimal but not mathematically infinitesimal. What they mean is that it is small enough for calculus operation to be taken over, but large enough to contain large number of atoms. That is the language I want to use. I want to think of a volume d3x in space or time, which contains sufficiently large number of atoms of space-time, which is the degrees of freedom, microscopic degrees of freedom, but at the same time small enough that I can use my standard calculus arguments. So this description of kinetic theory using distribution function recognizes discreteness, but yet uses continuum mathematics. And now an atom sitting at xi has an extra attribute pi, which you don't have in fluid mechanics. What is more, you can have multi-stream. At a given point x, you imagine several atoms moving in several directions. So at a given xi, you can have atoms with very many different pi. You can calculate velocity dispersion and fluctuations around the mean. What I am going to try to connect up is that this hg is related to number of atoms of space-time at xi with a momentum ni. Let me try to tell you how you do this. But before we do that, I want to get out of the way a little bit of algebra. Some of you were alert, would have noticed that if you use distribution function, xi and pi are independent variables. So you don't write things like di of pi. So if I have this na, this del n doesn't have a microscopic description. You would have more like this if this is like a momentum or velocity. You would have expected kinetic energy or the variational principle to have this structure rather than del n. But that is all right, because there is a very nice identity that this particular term which we used in the variational principle, except for a total divergence, is just RAB, NA and B. So what you want to get in dimensionless form by scaling things out is that you want to show that there is some kind of a term like this which has to come up in the variational principle from some microscopic description. So the idea is, how do we ever get this thing from a microscopic theory without knowing the full theory of quantum gravity? This one, this one, theta. Oh, theta is the expansion of the null surfaces. It is DI-NI. Okay, but what I am saying is that this term is ignorable. This is a total divergence on a null surface. So either this or this can be used, and I will try to obtain this term. Getting this term is equivalent to getting this term. Right. No, these points will get clarified once I finish, and we'll come back to these questions. No, it is a space density. Heat density as a TAB, LA, LB or Hg is a space density. Surface of what? No, that is the point. But it has a d lambda and d2 xi. At any given lambda, it is a two-dimensional thing.
Exactly, it's two-dimensional.
Yeah. I can integrate it on the null. Okay, why don't we get back to this? Let me try to define this from microscopes and then microscopic theory, and then we will get back to this. Fine. So how do I want to do this without knowing the full quantum gravity? We have already seen that what is vital is the discreteness, and the area LP square has to come in. So I'm going to start somewhere. I'm going to assume that the main purpose and the only purpose which I need of the quantum gravity is to introduce a 0-point length or 0-point area into the spacetime. So the claim is the following: you have a classical spacetime with a classical metric. Quantum theory has to renormalize this metric in some form. I'll try to make this more precise in the end if I have time. This renormalized spacetime should have a 0-point length. If you take the geodesic distance between 2 points x and x prime, in any classical geometry this will go to 0 when x goes to x prime. I'm going to assume that the effect of quantum gravity is to change this to plus some L0 square, which is of the order of LP square. So this is the only crutch from quantum gravity which I need, and there are several models of quantum gravity in which something like this emerges. Now, if you have a GAB from which I get this sigma square, then I need to get a QAB from which this should come. Yes? No, not in this form. I'm going to do this in Euclidean, and Euclidean it is sigma square plus L0 square. It doesn't break in Lorentz invariant. It is a myth that when there is a 0-point length, it breaks Lorentz invariance. It doesn't. It is t square minus x square plus LP square. You make a Lorentz transformation, it remains the same. It doesn't. Okay. So, coming back to this, so I have a sigma square which comes from GAB. So I want to write down what I call a quantum metric QAB, from which I'll be able to get this sigma square. This is something which we have done. I will come back to that in a minute. Fine. Once I have done this, then I expect the distribution function for atoms of spacetime to be something very natural. How many atoms of spacetime are going to be in a particular region? Either it should scale as the volume of the region, or it should scale as the area of the region. This is the minimal thing which I can assume. And it will turn out that areas are selected out, and these areas will give me the correct form. I think I should be able to do it. Maybe I will overshoot by a couple of minutes. Let's see. Fine. So those of you who are not familiar with this, let me just introduce a couple of concepts. Whatever you can do with metric in a Riemannian geometry has an alternate formulation in terms of what is known as Singe's world function. If I give you the geodesic interval sigma square of x prime for all x and x prime in a local region, it contains exactly the same amount of metric information. So what you can do with GAB, I can do with sigma. The equivalence is given GAB, you can compute sigma like this, and given sigma, there is a particular expansion, and in particular, if you take this and take the coincidence limit, you will pick up GAB. So you give me sigma, I will get you GAB, and then after that, I can do anything. It is a previously solved problem. Okay? So there's a complete equivalence between these two, but it is nicer to work with this sigma because we believe we know what quantum theory, quantum gravity does to sigma, but we don't know what it does to metric. So we go with sigma and then find out what happens to the metric. Also remember that I'm going to do everything in Euclidean, and in the Euclidean, sigma square going to 0 limit picks out the null vectors. I told you long back, and sigma square equal to 0 is the null curve, and when you go to the Euclidean origin in a local Rindler frame, it is going to pick out the null surfaces for me. So that problem is taken care of. So let me give you a kind of an illustration for this kind of a geometry. So the important concept in this is what is known as an equigeodesic surface. The simplest context is you take any point and you shoot out geodesics which are of some distance sigma, and if you are doing it in flat space time, you will end up getting a spherical surface. And in the adapted coordinate system, this is d sigma square, and sigma square times some S3 you will get. And both the volume and area measure, the area of this equigeodesic surface as well as the volume contained by the equigeodesic surface will scale as sigma cube. So when I want to calculate the area measure or a volume measure at a point, which is what I want to compute the distribution function of atoms at a point, I had to collapse these equigeodesic surfaces by taking sigma going to 0 limit, and both of this will vanish. Of course, that is what it should do, because this is classical geometry. It doesn't know any 0 point length. Of course, in classical curved geometry, it will get modified a little bit. Your equigeodesic surface will be some strange surface like this, and you have these curves, and there is an NA which is a tangent vector to this geodesic. So because there are different geodesics, there are different NAs at this point. And this will pick up, when you want to compute this, it will pick up corrections. And this is classical, this is Gauss. So if you compute that, you will find that both the root h and root g will pick up a correction which has this RAB, NA and B, which we are after. It is multiplied by sigma square. So when you tend sigma going to 0 limit to a point, all this will go away. Now you repeat this computation, throwing in a 0 point length. What we want to do is we want to assume that the number of atoms of spacetime at a point xi with an extra attribute which I loosely call momentum ni, it will scale either as a volume measure or the area measure of this equigeodesic surface collapsed to a point. So I want to just compute either this or this. Now it can turn out that both of them are divergent. The metric itself, the quantum metric of course is singular at every point. Okay, so what is this? G, in this particular coordinate system, there is no difference if you don't have any quantum corrections, because you are using this coordinate. In general, G is the d-dimensional metric, H is the metric on the cross section of the equigeodesic surface. It is like an area versus volume. Okay, now you do this quantum mechanically, and what you find is the following. You find that the volume measure goes like this, and it has a sigma sitting in front, which is the only thing you should concentrate on. While the area measure goes like this without that sigma. Now I am working in d is equal to 4, but the results extend to arbitrary d. Now this is something which we wrote up recently, pointing out that in this approach of 0 point length, all d-dimensional spacetimes in the Planck scale becomes 2-dimensional. So there is a sigma d sigma. So the volume scale is sigma square. What is more important, when I take the limit of sigma going to 0, I get a finite number. So this is a very strange kind of a geometry where every point has no volume but a finite area, so to speak, and you get a root h which has exactly this factor. So you just scale out the parts which are anyway present in flat spacetime, and you define your distribution function by this. And this L0 square you identify, in order to get the correct Newton's law in the end, you identify with this 3 over 4 pi. So what you get as a final result is the following. The area measure of a renormalized spacetime gives you exactly what we need, but with an extra 0 point contribution, which is 1. That is important because these things are coming from positive definite quantities at the lowest order. And so the leading order correction term which we are picking up is this, but this has this important minus sign. It does come with that minus sign, and there is a quantity here in order to make sure that everything works fine. This 0 point contribution is very important for a completely different reason. Because I told you way down that my approach tells you that there is an undetermined constant in the theory, which is the cosmological constant. But the theory is duty found to tell you what the value of that constant is. Otherwise, the theory is sort of not there completely. So if you give me an evolutionary model of the universe, there must be a way I can fix the value of lambda. And for that, I need the information that the degrees of freedom on a Planck 2 sphere is 4 pi. So this is something which we have done some time back. Some of you might have heard me speak about this. Just to remind you, the current picture of our universe uses three distinct phases. One is the inflationary phase with one constant. This is a numerical constant, which is the density at that time. Another late time accelerating phase with another constant. And then in between, in the matter radiation phase, there is another constant, which is the density at the time of matter radiation equality. If you give me these three numbers, I can write down in an epoch invariant way the Friedman equation, and the entire geometry of the space-time is fixed by these three numbers. What happens is that there is a conserved quantity in this theory, which is the total number of modes or degrees of freedom which traverses through this phase. So we called it cosmin, and we showed that if the Planck sphere has 4 pi degrees of freedom, you get a very remarkable relationship between these three densities. In conventional cosmology, these three numbers are postulated. There is no relation between these three. Rho inflation, rho equality, and rho lambda are three independent constants. What is observationally well determined is rho equality and rho lambda, as a result of which, using this, I can predict what rho inflation should be. But theoretically, rho inflation and rho equality will come from high energy physics. Once we know what drove the inflation, and once we know what is the dark matter content of the universe, then this equation predicts for you the value of the cosmological constant. So whenever I used to give this emergent gravity talks in the past, like 5 years ago or something, people used to say, oh, that is very nice, it nicely tells you gravity is like thermodynamics. But what is new? I mean, we knew everything about this. So then we came up with this. This relation doesn't exist in any other approach I know of, and if you put in numbers, it matches to some 1 part in 10 to the 5. Okay? And it predicts the rho inflation to within a factor of 5. So it is a disprovable theory. If biceps or any of its clones tells you that inflation took place outside a band of 1 to 7 into 10 to the 15 GeV, this theory is wrong. So there is a prediction that inflationary scale has to be like this in this area, this universe. I had to explain to you in person, because or you can read up this paper. Okay, so it comes from there. Okay, so I'm almost at the end. So what are the open questions? The key open question in my mind, about which I want to make a bit of a speculation, is the matter sector. The problem which haunted Einstein continues to haunt us. One side is very beautiful, GAB, geometrical, then you have to equate it to TAB, absolutely dirty, we have no clue what it is. So it is somewhat like you having a piston and a gas which is hitting the piston, and you can compute the fluctuations in the pressure on the piston because of the discreteness of the gas, but you don't take into account the discreteness of the piston. So we do have to interpret this from some microscopic principle. Second, the entropy maximum principle is very different from a maximization of an action. Maximization of the actions are rooted in quantum mechanics. You have exponential I times A, phase oscillates when h cross goes to 0, selects out delta A equals 0. Entropy maximization comes from e to the power s, and they need to be reconciled. One way of doing this is to do everything in Euclidean, because the Euclidean action does not have the I factor, and you can do that. Then, as someone was raising the question, I mean, there is some Cauchy kind of an issues which can be done with this distribution function itself. You can ask how that evolves. There are other geometrical structures which could lead to the same result, and one needs to explore them. You need to generalize this to Lovelock models, which would require RAB being replaced by this. There are some first result which shows that this does work. So I want to end with a bit of a speculation. What I think is going to happen eventually is that the distribution function for number of atoms at a point xi with an attribute Na is actually going to go like this. And what we have picked up is the first two terms, 1 minus this quantity. In this approach, the field equations finally is going to emerge somewhat like this. If you calculate the cross correlation of Na NP, you will get RAB inverse. Because it is RAB inverse, what you are going to get is this TAB Na NB averaged either over a probability distribution or over the Euclidean action with some measure, is going to sort of, when the correlations are neglected, is going to be some TAB expectation value times NAB equal to 1. which will tell you two things. First, it has some kind of a Machian analog that TAB going to 0, you will get 0 equals 1. No matter, there is no geometry, no description, nothing, because I told you that both matter and geometry are quantum mechanical, and you can't have one without the other. In some sense, matter has to emerge from geometry that is closely tied together. This differentiating matter from geometry, writing GAB equals TAB, is frowned upon in this approach. And the second, you don't have an LP going to 0 limit either, that I have already emphasized. Geometry and matter are intrinsically quantum mechanical. You kill LP, you will get 0 equals 1. So this is what I think is going to finally emerge. So let me just summarize. Demanding that gravity is immune to 0 level of energy is a very powerful principle which allows you to construct a variational principle which selects out for you Lovelock models of gravity and Einstein gravity uniquely in D equals 4. This variational principle, as well as geometrical variables and the evolution equation, you no longer has to write GAB equals TAB. You don't have to have geometrical interpretation. You can write everything thermodynamically, and which is very interesting. And if we take the number of atoms of space-time at any given point as proportional to the area measure with a 0-point length, then you do get this corrected variational principle. And what is more, this theory makes a prediction. You have an equation which relates three densities, three observable densities in the universe, which did not exist before. No other formalism gave you that relation, and that relation can be checked against observations. Thank you. Yes.
And I wonder how the gravitational wave picture fits into it, because we know that they are not captured by RAB.
Yes. That's right. That's right.
So why are you not including that in
Yeah.
your answer?
So the question is, firstly, there are manifolds with RAB, Ricci flat RAB equal to 0, which are curved, right? In this approach, and in some versions of Mach principle, one would say that such manifolds are not physical. That is, if there is no matter, if there is no TAB, and you solve for RAB equal to 0, then you should only pick up flat space-time. And in this approach, there is no such thing as flat space-time, because everything is quantum gravitational. So I believe that in this approach, it is rather consistent that mathematics drives me to this. We did look for whether there is an RABCD corrections to that. We found none. So it is the maths which leads us to conjecture this. So I will go with it, and I will claim that this is a version of Mach's principle.
So you're saying if gravitational waves are discovered, that this is theory now?
No, because gravitational waves are not solutions to RAB equal to 0, even though people keep saying that, any more than electromagnetic waves are solutions to box mu equals 0. They are not. Electromagnetic waves are at some level emitted by something and then detected by something. There is source. Gravitational waves are spacetimes with source. It is just that in between they propagate with RAB equal to 0. For that, RAB equal to 0 is how you get short sail metric. I don't even need to go to gravitational waves for that. So you can say that if short sail metric is detected, this theory should be out, which is not the case. So I think if there is no matter anywhere in the universe, then you have a contradiction if you find something like that. It's a very peculiar thing about our universe that we never observed flat space-time. Flat space-time is one thing which we know doesn't exist. Nowhere we have seen flat space-time, and that is what this theory tells you. Yes.